Hey there, dude bros, it's Chili here, and welcome back to the Advanced Tutorial Series Lesson 3. Today we are talking about rotation. Now, rotation is a very important topic in games programming in general, and specifically in 3D games, right? It's basically the key to 3D games programming, in my opinion, 3D graphics. If you don't have rotation, you don't got shit. So we're going to be handling that with vectors and math and all sorts of good stuff. No escalators required. But before we cut to the chase there, head to the main topic, we got another edition of Chili Done Fucked It Up. So what happened this time? What went wrong this time? Well, it's really interesting here. A little subtle thing. You remember polyclosed last lesson and the loader that we created to parse DXF files and load the vertices into a collection here, a vector collection. And yeah, so we load up the vertices from the DXF file into this collection, and then we use a reference to that collection via get vertices. We use a reference to initialize the collection in our polyclosed here. So we load the vertices from the DXF into here, and then we copy from here into here. And what I did at the end there was a little optimization. I added std move, and what that would do is instead of calling the copy constructor and copying every item into here, it basically just moved the contents of this container into this one, basically making this one's pointer point to this one's contents and this one point to nothing. So it just moves it all over, and that is way faster than copying. So that's good, that's all fine. I explained that in the last lesson. However, there was one little thing that was bothering me, and I'm gonna debug into this mother. Step in, step out. And don't do that. This one. So here we are at get vertices, and we return the constant reference to vertices. And now if I step in, I should enter the move constructor. And here's vector constructor. Construct by copying right. Yeah. So we're not getting our move semantics here, our move construction. Now, why is that? Well, if those of you intrepid enough can pause the video and try to figure out the mystery for yourself, it's a good exercise in debugging. But I know most of you aren't going to do that, so I'm just going to tell you that it is this constant here, right? Because if we return a constant reference, that means we can't modify this thing. But if we move, then we're emptying this thing, which is definitely modifying it. So there's a discombobulation there. I couldn't think of the word I was going to try to say, so I just said discombobulation. Yeah, a discrepancy maybe? I don't know. Anyways, so the problem is the constant. We get rid of the constant, and we get another error. And if you're again, you can try to pause the video and try to figure out what this error is. But I'm going to tell you right now, it's this constant. You can't return a non-constant reference to a member variable if your function is constant, because a constant function is saying, I'm not going to modify anything in this object. But then returning a reference is saying, giving the caller free rein to modify that variable. So you got to get rid of both constants. And if you do that, and we step in, we give her the old in out, hardy har har. And we got our vector constructor, construct by moving. So now we get our proper move construction. So, and the funny thing was, when I was writing this, I was like, I don't think this is going to work. But I did it anyways because I figured it would be a teachable moment, right? And then it did work, and I totally forgot about it until the end when I finished recording. I'm like, hey, whatever happened with that move construction? That was supposed to give me an error. But apparently, the compiler doesn't give you an error. It just says, this guy's dumb, I'm going to do what I want to do. And it doesn't even tell you bullshit. Actually, Maybe there's a warning and I just didn't catch it. 2 warnings. Nope, but nothing about the move. So, yeah, weird. Weirdness on weirdness there. So, and just to prove a point, if you remove the standard move from here and you give her the old in out, you get, again, copy construction. So you need that, if you want move semantics, you need to actually go in here and put in your std move. It's like I always say, the more STDs, the better. Gotta catch 'em all. Okay, so yeah, so that was that was this episode of Chili Done Fucked It Up. One more thing, I figured out how to get your debug variables back. You gotta be in debugging mode, and then you go to debug and you can access all of your sweet ass windows, all this good stuff. GPU threads and it's making me horny just thinking about it. So that's that for any of you guys who run into that same problem. But yeah, that's it. So you can't move constants, go figure. Oh wait, I wanted it this way. I did it the wrong way. I made the bad game. Okay, so that was Chili Done Fucked It Up, and let's move on. So rotation, yeah, so in order to handle rotation, in order to treat this topic, we need to have a basic understanding of trigonometry, of sine and cosine. So that's what I'm going to do in the beginning here. I'm going to give you guys a little crash course in sine and cosine. In order to facilitate, some of you guys might already know trigonometry very well, and if you know trigonometry very well, and you know radians, the degree of angle or the measure of angle known as radians, then you can skip this section. Just look on this little bottom left hand corner here. I've written a nice little trig in green here, so you can just kind of fast forward to the video until this disappears, and then you'll know that I have completed the trig part of our discussion and have moved on. So, trigonometry. What is it about? What are we doing? What are we about in our trig talking stuff? Well, in order to talk about trigonometry, we have to know what an angle is. And I know you're saying, Chili, I know what a fucking angle is. I'm not like 3 years old. But I want a very in-depth, I want to make it clear what an angle is. Like, people think about what is an angle, they think, well, you take 2 lines like this, and that's the angle, that's the thing there. But what does that mean? What is an angle? Angles are best discussed in terms of circles, right? When we can describe a point on a circle, let's say you want to describe any point, we could say, start here, start at this point here, and go along the circle, let's say go 1/4 way around the circle, and here's another point in the circle. And that's basically what angles are doing. It's saying go this much around the circle from some starting point. That starting point is generally here unless otherwise stated, on the positive x-axis. Now, what you guys are normally used to, right, is something called degrees, right? 90 degrees would be this much around the circle, okay? And yeah, that's fine if you are a savage, but for us civilized people, we tend to have more discerning tastes on our unit of angle. Now the question is, why is this 90 degrees? Why is it that all the way around a circle is 360 degrees. Why? That seems like such a random number. Like, why pick 360? Why not pick 100? And then you could say 50% around the circle is halfway. Why do you have to go 360? Well, that comes back to the Sumerians. Sumerians like to count in base 60, which is also known as, I shit you not, sexagesimal. How dirty is that? Those dirty Sumerians. So yeah, base 60. And that is why we have 60 seconds in a minute and 60 minutes in an hour. So it's a lot of things. It comes all from those Sumerians and their crazy brain programs. If you've ever read Snow Crash, you know what I'm talking about. So yeah, it's fine, but it's also kind of retarded. Base 60 has some good advantages, but it's still fucking dumb. It's still super arbitrary. Now, I'll tell you what's not arbitrary. How about halfway around a circle, we will define that as being 3.14159, otherwise known as pi. Now, you may look at this and say, what the fuck? That is retarded. I mean, 180 isn't no great shakes, but it's way better than 3 point whatever the fuck. And I would agree with you, except that your opinion is stupid, because this is the best way of defining angles around a circle. Take a radius. Take this circle's radius. This is a unit circle, by the way. So that means that this circle has a radius of 1. So take that radius of 1. And now lay it out along the circumference of the circle. There we get 1 time around the circle. We go 2 times around the circle. I need a different color. Let's try teal. We got 3 times around the circle. And last but not least, we'll go with blue. Wait, I already did blue. I'm running out of colors, bitches. And this one goes 0.14159 yada 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 times around the circle. So if you take the radius, it goes around the circumference exactly 3.14159 blah 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 times. In other words, the ratio of the radius to half the circumference, or I would say half the circumference to the radius, is 3.14159. And that holds true for any circle in the universe ever, if it's a true circle. So that is pretty crazy. That's pretty awesome. And that is a much better way of defining angle. You define angle by how many times the radius goes around the circle. So let's undo all this bullshit. So in that case, my friends, all the way around the circle is pi radians. I fucked that up. Halfway around the circle is pi. Quarter way around is pi over 2, and so forth and so on. Now this way of representing circles is the way that it works best in mathematical equations, and this is also the kind of angles that the standard math library in C++ uses. If you pass it an angle in degrees, it will give you a fucked up answer, because it'll be like, what the fuck? What? I'm no savage. Give me fucking radians, you animal, you heathen. So you better fucking learn radians, because that's all I'm gonna talk in. Fuck you and your degrees, man. Fuck you and the horse you rode in on. So radians is good. Now that we've talked about radians, we can talk about trigonometry. First, I need white. So trigonometry. Try try to learn this shit, you bastard. Ha! So trig means triangle. Metry means measuring. No means no fucking way you're gonna do 3D games without this bullshit. Understood? Then, forget this because fucking learning trigonometry by triangles is dumb. Learn it by circles because circles are way better than triangles. Everyone knows this. So, how are we going to learn trigonometry by circles? Very simple. Remember back in the day? Remember when we did x squared plus y squared is equal to r squared, the relationship that describes the circle? You know, that let us find, for example, if we had an x, we could find the corresponding y values and plot them on the circle and draw it. That's nice. But you know what would be nicer? Or at least as nice, but in a different way? What if we could find the x and the y on a circle given some angle theta? Well, let me tell you, friends, that is what cosine and sine is all about. So, if we've got a coordinate here, and we'll call it cx for a circle x and cy, well, that coordinate, my friends, can be calculated as follows. Cx is equal to cos theta. Cy is equal to sine theta. Very simple. Sine gives us our y, cos gives us our x. Now this is only for the unit circle. The unit circle, my friends. But this is how it works. That's how cosine and sine works. It's very simple. Let me show you a demonstration. Not that one. This one. Here it is. We've got our unit circle in radians because we're not savages. And as I move the angle here, the blue and the red lines give us our sine. That's our sine and our cosine. Forget about the green line. It doesn't matter. Fuck it. Fuck tangent. But yeah, blue and red gives us our sine and cosine. You can look here. Here's a graph of it on your standard, graph paper of the functions. So sine and cosine, they give us our blue and red x and y coordinates. So it lets us turn angles into coordinates. Very useful, my friends. So, what's the next thing Chili's going to talk about? Okay, now you also have at your disposal, if you so choose, another function called arccos and arcsine, sometimes also known as just acos or cos with a little -1 there, inverse cosine. And what that does, it does the exact opposite of cos and sine. So given an x value or a y value, it will return an angle. Okay, so for example, let me think here. So cos -1 of, not of theta, ooh, I fucked it up, of cx is equal to theta. So we can plug in an x value and we get an angle corresponding to that. All very good. Very delicious. Delicious. Okay. So it's the inverse. It undoes the function of cos. For example, cos -1 of cos theta is just equal to theta, right? This one and this one cancel out and we just get theta. This will be useful a little later on, and that's why I'm talking to you about it, but we won't use it that much. Now, what else do I want to talk about? One more thing. So cosine and sine, it gives us what? It gives us our a point on the circle. But imagine a point here, 0.10. And imagine we want to rotate that point to some arbitrary position. We want to rotate it by theta degrees. Well, that's just exactly what we had before, right? It's just, we'll call this P2. And it's just P2x. What is it now? Tell me, everybody. Cos theta. And P2y sine theta. So if we're rotating from this position, we just use our cosine and our sine directly. So you can kind of already get an idea of how cosine and sine kind of jive in with rotation. Now, what if, my friends, we have a circle that is not a unit circle? Let's take a look at this circle here, which we're going to pretend is a circle, first of all, not like some kind of potato, and also that it is a radius, we'll say 2. So now we've got here, we've got a point on this radius 2 circle, quote unquote circle, and how do we find this point? Well, we can find it on the unit circle very easily, right? It's just going to be, the point is going to be, we'll say P, X, this will be P, this will be Q, point P, point Q. So Px is going to be equal to, again, cos theta, Py is equal to sine theta. Now, the relationship between these two triangles means that this one has a hypotenuse that is equal to 1. The length of the hypotenuse is 1. This one's hypotenuse is 2. It's double the size of this one's. So if you double the size of a hypotenuse, keeping all the angles the same, you're going to double the length of the other sides. So Qx is just going to be double Px, which is 2 cos theta. And Qy is going to be 2 sine theta. Very simple, right? So for a radius r, for a triangle of, or not triangle, a circle of any arbitrary size, x is equal to r cos theta, y is equal to r sine theta. And that, my friends, is the magic of sine and cosine. Now, what else do I want to talk about? SOHCAHTOA. Okay, this is the way that most people learn trigonometry, and it's going to be useful in a derivation that I'm going to do, so I'm going to talk about it a little bit here too. Let's get me a layer. Fuck. I turned this trig thing off. I just fucked everyone up. I told them that, oh no. Whatever. I don't fucking care anymore, dudes. This is my 3rd time recording this bullshit, and I am not gonna start over. So anyways, what was I talking about? Oh yeah, SOHCAHTOA. So say you've got a right angle triangle. This is your hypotenuse. You've got an angle theta. Now, with respect to this angle, this is the opposite side, and this is the adjacent side. And there you have your right angle triangle defined. And there's a little special magic words called SOHCAHTOA. And what that means is sine theta is equal to O, opposite over H, hypotenuse. Cos theta is equal to A, adjacent over H, hypotenuse. And the other one is just tan theta is equal to opposite over adjacent, but fuck it. We don't need that bullshit. We just need SOHCAH. So yeah. And that's just a relationship for any general triangle. Because if it's not in the standard position here, then you might have trouble figuring out which angles are doing what. And I mean, if you take a triangle in standard position, you see that H is just R, and this is theta. Opposite is just X, and adjacent is just Y. So, for example, take cos theta. Cos theta would then be equal to I fucked it up. Ooh, chili fucking it up. Opposite is Y. Adjacent is X. Cos theta would be equal to X over R, or in other words, multiply both sides by R, and you would get X equal to R cos theta, which is what I said before. So these things are equivalent, but knowing this definition will help you in certain situations. So yeah, SOHCAHTOA. And it's fun to say too. Just say it. SOHCAHTOA, SOHCAHTOA. Okay, why am I doing this? I could just delete this layer. Alright, 25 minutes in the video, and I've finished trigonometry. I think we're in, except for the fucking up with this trig thing, I think we're in good situation. So now we finished trig, and we are ready to go into rotation. Oh, that's the wrong one. Let's try this one. Oh, that's the right one. So imagine we have... Imagine all the people... I can't remember I don't even know the name of that song. Yeah, so we've got a point P, and we want to rotate it by an angle theta. And the resulting point, we'll call that point Q. So how do we find Q? We want to find QX and QY, the X and Y coordinates of our new point Q. Well, again, going back to our definitions, we know that these radiuses are going to be the same because if you're rotating a point, it's going to form a circle, and 2 points on the circle are going to have the same distance from the center, the same radius, okay? So, we can say, let me just go back here, Control Z. We can say QX is equal to R cosine, and it's theta plus phi. Or is it phi plus theta? I'm going to say phi plus theta. And again, QY is equal to R times sine phi plus theta. Now, phi is the angle that our original point makes with the standard position thing. I can't forget what it's called. 1 second, I think I have a web page. Standard position of an angle, yeah, whatever. The angle it makes with the positive x-axis. Now, we don't know that. And we don't know R. But we can calculate both these things. So how do we calculate phi? Well, first let's calculate R, because that'll make my life easier. R is very simple. That's just the square root of px squared plus py squared. Now that we have R, we can calculate phi as equal to we have to use inverse cosine, right? And we have to divide px by r, right? SOHCAHTOA, adjacent over hypotenuse. Adjacent over hypotenuse. There you go. And once we have phi, and once we have r, then we can plug them in here and get our qx and qy, and we're done. And that is one way that you could rotate this point over to here. It's a very dumb way to do it. I don't recommend it. Why wouldn't I recommend this? First of all, inverse cosine takes a long time to calculate on a computer. Also, square root isn't any great shakes either. These two things are going to slow us down. And then we've got, on top of that, we've got to calculate a sine and a cosine. So we've got to calculate a sine cos, we've got to calculate inverse cosine, and we've got to calculate a square root. That's too much dumb calculations, because we can do this way faster if we're smart. Now, how are we going to be smart, you ask? How would Chili be smart? Well, I want to just note that P, even though we already know Px, we can write here Px is equal to R times cos phi, and Py is equal to R times sine phi. So I'll note this here. Qx is equal to r cos phi plus theta. Qy is equal to r sine phi plus theta. Now, here is where the magic comes in. This derivation is magical because it uses crazy math magic. And let me just show you. The math magic is the angle sum identity, which basically says that, for example, the sum of, or the cosine of the sum of two angles is equal to cos alpha times cos beta minus sine alpha times sine beta. So you can, these two expressions are equivalent, and you can expand this one into this if you wanted to. Now, why would you want to do that? This looks way more complicated than this. Well, let me just, here we go. Let me just show you why you'd want to do this bullshit. So, r times cos phi plus theta. So here we can say Qx is equal to r times, and we're going to expand from those identities, so we're going to say r times cos phi cos theta minus r sine phi sine theta. And here we go Qy is equal to r sine phi cos theta plus r cos phi sine theta. Okay, so we just made this way uglier. But now we can be tricksy. Because look at this. R cos phi, R sine phi, R sine theta, R cos theta. What does that remind you of? Does that remind you of these two things? If it does, then you might be smart. Maybe. So let's go R cos phi, R cos phi, R cos phi. I'm going to make it all color-coded because we like colors. So we can replace px and py into here and here. And that will get rid of both of r and phi from our equation, so we don't have to calculate either of those. So now we have Qx is equal to r cos theta. That's x. X cos theta minus, well, wait. I kind of fucked it up. Alright, I fucked that up. It's not x, it is px. Pardon my French. Px cos theta minus r, not r, minus py sine theta. And qy is equal to p, this is sine, so py cos theta plus px sine theta. And there you have it, my friends. We've got our final derivation right here. Now this one has the advantage in that we don't have to calculate cos, or we don't have to calculate the inverse cos, and we don't have to calculate the square root. None of those things are important. We get our qx and our qy directly from our px, which we know, px, py, which we know, and our theta, which we also know. So we don't need to calculate any of those intermediates. It just automatically gets into this solution. So that's like fucking money for free, people. Now this is the actual equation or formula that we'll be using in our code. But it's kind of difficult to understand, like to visualize in your head what is going on with this rotation, because we used a little bit of mathematical dark magic here to kind of magic our terms into the way we like them. So I have one more derivation for you guys. This one's special for you. And it is based on vectors. So let me see here if I can figure out how I'm going to handle this. This is where I fucked up my last recording because I couldn't get it right. So I'm going to lose this layer, and I'm going to copy this layer, and I'm going to copy this layer. Wait, fuck that. Stop it. I'm going to copy this layer, and I'm going to show it this one. I'm going to show this layer, and I am going to unlock both of those layers. All right, so we've got a couple of vectors here. Now these are special vectors. I've talked about them before. Let me talk about them again. So this vector here, I better add another layer. This one is called X hat, and this one is called Y hat. Why are they called X hat and Y hat? Well, they are size, their length is exactly 1, and they point in the X and the Y directions only. Now you can write any arbitrary vector, any vector v, as the X component times X hat plus the Y component times Y hat. So by scaling these two vectors and adding them together, you can get any two-dimensional vector you want. Now what we're going to do is we are going to define a function or an operator that works on vectors. We'll call that function rot theta, which will rotate a vector by theta. And we're going to define that function. We're going to find the solution for the special vectors x hat and y hat. So rot theta x hat. So what is that? Well, let's have a look at vector copy here. I'm going to copy this one. I copied the wrong one. So I'm going to garbage it, and then I'm going to copy this one. Yes. And then I'm going to transform this one, and I'm going to rotate this vector a little bit. I'm going to accept that, and I'm going to move it here. So let's say we're going to rotate this vector from here to here. I think I want to color this vector. So let's color it red. Can I? Yes, I can. Oh yeah, it's working good. Okay. So we'll hide this vector. So we want to rotate from the white vector to the red vector. We're rotating by an angle of... Jesus Christ. An angle of theta. Oh, and I don't want to write on there. So don't want to write. There we go. So we'll do rotation by theta. So how do we get that? Well, since this is just our point in standard position, the answer is going to be clear, right? The x is going to be cos, just cos. So we go cos theta, and we multiply that by x hat, because that's the x component, plus now there's going to be a y component. Before there was no y component, now we're going to get one, and it's going to be sine theta times y hat. So there you go. There is our solution for rotating x hat by an angle theta. Now we want to let's hide these vectors here. Now we've got another one here. I'm going to copy it, and then I'm going to rotate it a little bit. And there you go. Beautiful. Let's do that. Let's get red. And we'll color this vector in here. Lovely, lovely. I can't color this bastard worth shit. There we go. So let's try this again, my friends, but now we're going to rotate y hat by an angle theta. So let me get my white here, write theta there. We'll also delete theta from over here. So rotation by theta of y hat is equal to what? Now this is trickier, my friends, because now we are no longer in standard position. So we can't just say x is cos theta, sine is y theta. We're not allowed to do it quite that simply. But let's draw a triangle here, and let's use our SOHCAHTOA powers. Okay, so here our angle is right here. So our opposite is going to be here, which is going to be our x value, and our adjacent is going to be here, which is going to be our y value. So let's solve for our x. Sine is opposite over hypotenuse, right? So let's just write here, sine theta is equal to opposite over hypotenuse, and the hypotenuse is 1 because this is unit, this is a basis vector on the unit circle, length is 1. So sine theta equal to opposite. And now this is our x value. So that means x is going to be sine theta. But although the length is sine theta, it's moving in the negative direction, so we have to put a minus sign here. Now we go plus. Let's erase this bullshit. So now we've got to look at the other one, which is going to be adjacent over hypotenuse. So cos theta is equal to adjacent over hypotenuse is equal to a, right? And that's just going to be cos theta times y hat. And yeah. So let's erase all this bullshit here. Now, so there's our solution for rotating the x hat and the rotation of y hat. Rotating x hat gives us this vector. Rotating y hat gives us this vector. Now, why, you might ask, why is Chile making us, define this rotation function for only x hat and y hat? There are going to be very few times where the thing that we want to rotate is exactly x hat or y hat. Well, let me just see if I can enlighten you a little bit here on what we're about. So now we want to rotate just some arbitrary vector of arbitrary length. So where is our thing? I like this vector. I think I will keep it. This one. There we go. So yeah. We'll take this vector. We'll transform it. We'll rotate it a little bit. And maybe we'll scale it in this direction a little bit. Just a little bit. There we go. So we've got our vector here. And we want to rotate it by theta radians, by an angle of theta, to get our new vector, whatever. So how do we do that? Well, let me tell you how you do that. We're going to give our vector a name v. So we go no, that's no good. Rotation by theta of v is equal to rotation theta of vx times x hat plus vy times y hat. So here's the first step. Rotation of the vector is just rotation of the sum of the components of the vector. Now here comes the magic. The next thing we can say is that this is equivalent to rotating the x component and adding that to the rotated y component, vy times y hat. Now, why can we say this? Well, imagine, let me get some vectors here. What about this one? There's a good one. So let's get the components of this vector. Yeah. Scale that down a little bit. Scale it up a little bit. Yeah. There we go. Seems good to me. There we go. So there's the y component. We want another one for the x. So I think we'll just copy this here. Make it visible. The layer is locked, so we'll do that. Bring this one over here. Transform it. Scale it here. Enter. Okay, so this vector here what shall I do? I think I'm gonna color this in. So this vector here is the x component, the magnitude of the x component times x hat, right? And do I got it? Yeah, I do. Give me this here. This one is the y component, right? So this is vy times y hat. This is vx times x hat. Now what this is saying is that rotating the sum of the components, this is the sum, rotating that is the same as rotating the individual components and then adding them together. Now, is this true? Well, we can try this out. Let's try it out. So where's my original vector? Is it this one? There it is. Oh, and it also has the... Ooh, this is going to be ugly. Again, Chili comes in with his fucking it up. But we're going to do it anyways. So, let's rotate the components first. So where's the first component? Here it is, the x component. So what we're going to do is we're going to transform this one. And we're going to rotate it by 20 degrees. So where's my... Here it is. 20 degrees. There we go. So do you like it? Good. So there's our original vector rotated by 20 degrees. Now we're going to take the y component here. There it is. Transform that. And we're also going to rotate this one by 20 degrees. There we go. And now we add those together. So this should be, if we rotate the white vector, it should also point here. If it doesn't, then that means that this is not true. We can't do this. So let's take the white vector. This is going to be ugly. Transform it. Rotate it by 20 degrees. There we go. Beautiful. And if I move it into place, you will note that it does indeed basically match up with the two rotated components. So what this proves is it proves that rotating the resultant vector is the same as rotating the components and adding them together. So we are allowed to say this. Let's move on. We're not done yet. Now we add a new, well, Jesus Christ. Now we add a new line here, and we say that Vx, rotation by theta of x hat, plus Vy, rotation theta by y hat, this is equal to this. So what this is saying is we're allowed to take this this scalar outside of the function. And again, what does that actually mean in words? Well, it means that there's no difference between scaling first and then rotating, or rotating first and then scaling. And that is also true. I think you can understand. I don't even have to make like a fucking like special diagram for this. It should be pretty easy to understand that rotating a vector and scaling a vector are different. I mean, they don't affect each other in any way. So for example, if I were to take this vector, or first take this vector, scale it to this vector, and then rotate it to here, that would be the same as if I were to take this vector, rotate it here, and then scale it by the same amount. It doesn't matter the order in which you do those things. They are order independent for this function. Now let me say something before we move on here quickly. If this were a different function, we couldn't do this. For example, if the function was a square root function, the square root of x plus y, we couldn't say that this equals square root of x plus square root of y. Or if this were square root of ax plus square root of ax plus by, we couldn't say that this is equal to square root of, ax plus by equal to a square root of x plus b square root of y. These, you could not do these things with square root. It doesn't have that property. But our rotation function does have that property. And if you visualize the situation, you can see that these properties hold true. There's names for these properties. I forget them. But, so yeah. So now we have our Vx times rotation theta of x hat and Vy times rotation theta y hat. But that, my friends, is just these functions here that we already defined. So we can plug these in and we can get Vx times cos theta x hat plus Vx times sine theta y hat plus Vy, where is it? Vy is here. But this would be negative because it's minus sign, right? So negative Vy sine theta x hat plus Vy cos theta y hat. And then we collect together our x hats and our y hats, and we would get Vx cos theta, where is our other x hat? Here, minus Vy sine theta x hat plus Vx sine theta plus Vy cos theta y hat. And this is exactly the same as what we got from the sum of angles formula, only written in a more vectorized form with the basis vectors. So it's the same equation, same formula, just a different derivation using the properties of vectors, I guess. It's a vector explanation of that stuff. And this explanation is, at least to me, is much easier to visualize. You visualize rotating the individual components. Fuck it. Now I don't know how to return this. Like that? Okay, good. We're a little bit off here. There we go. So yeah, you visualize rotating the individual components and then adding them together. And the individual components, the x and y, their rotations can be derived easily. So yeah, that's it. Here's our magic formula. There's your 3 derivations as promised. And now it is time to put that shit into code. So, where are we going to handle this? Well, to start off, I've got plans. Let me tell you, I've got plans. Chili's got plans. But to start off, we're going to go into vector. We're going to outlining, collapse all in block. That didn't help. Let's try it again. Outlining. I don't even know anymore. Outlining. Collapse to definitions. There we go. That seems to have solved my problems. We're going to add a new function in here. Inline. What should it be? I guess the question is, should the rotation of the vector, should it be a mutator? Should it change the object? Or should it be a non-mutator where it just creates a new vector object? Now, and that's where I have trouble. Let me think here. Let's take a look at how our thing works. Which one would we need? So in polyclosed, for drawing it, we do position. I think we want a new one. So we'll go back. To vec2. We'll call this one rotation. I feel like the word rotate means you're actually rotating that object itself and mutating it, whereas rotation means like you're getting the rotation of that object, not modifying the object itself. So we go rotation, and what we want is we want a constant float angle. And this will be a constant function because it doesn't modify the object. And what are we going to do here? We'll go with, I guess, underscore vec2. Now I almost feel like type T. We could make the, yeah, I guess we'll make the angle. We'll make it the template parameter. That way this will work for doubles and floats the same. And we want vec2. Where's my angle brackets? T. We'll call this the result. And result dot x is equal to I don't want this, do I? What do I want? Here's what I wanted. So x is equal to x cos x minus y sine, so x cos theta minus y sine theta. So just x times it doesn't, this is interesting. We're going to make the angle float for now. I know it's bad because, yeah. It's hard to explain, but I can use a templated version of cos that will work for floats and doubles, but in order to do that, I would have to change the way I handle math functions in here. And I don't feel like doing that right now. So I'm going to hardwire this one to work only with float angles. So cos f angle, I think it was a minus sine f angle y times sine f angle. And result dot y is equal to, let's go back here. There we go. X times sine plus y times cos. Simple enough. X times sine f angle minus y times cos f angle. And then return result. And that should give us our rotation, unless I fucked something up in the derivation, which is possible. But if it is, I'll just look up the correct formula. Build. I should build that, make sure it doesn't barf on anything. Okay, that's fine. Now let's change our polyclosed. Draw. So we have a position. Let's go no, we want float angle. And now what we want to do is we want to go to I, pointer to rotation angle plus position. So we want to rotate and then translate. And here, I plus 1. Fuck that. Fuck it. There we go. Rotation, angle, and there you have it. Here we have back dot rotation angle and front dot rotation angle. So here is the moment. Oh wait, now we have to go to game, and we need an angle in radians. So let's try to rotate it by 0.7. Because that's kind of an angle thing. Probably close to 45 degrees. Let's see if it worked. And it sort of didn't really work, did it? This one kind of smushed it up. So we go so let's see here. X times cos, x times sine. Oh, this one's minus. It should be a plus. So there's a first problem. Will this solve the problem? Yeah, it seems to have solved it. There you go. There's your proper transformation. We get our weird errors again. Bam. Whatever, shut up. Let's go to game. Let's change the ship to our good ship model. There we go. Perfect. Look at that. Now we can do other things like, for example, we could go into game.h. We could add a variable float angle is equal to 0. Then we go to game.cpp, update model. Angle plus and equals 0.1. And we'll write angle in here. And there you go. If that isn't beautiful to you, then I don't know what could possibly be. Because I think that's just the best thing in the world. Spinning penises. Gotta love it. So, yeah. And there's one more thing I could just add just to... we have to calculate cosine and sine a total of 4 times, but that's dumb. We can go float. Float cosine is equal to cos f angle, and float sine is equal to sine f angle. So we pre-calculate those. Then we can put cosine here, put sine here, and sine there. There we go. And that will hopefully speed us up a little bit. And there you go. Same thing, so no problems. But that, my friends, is rotation in a nutshell. As you can see, it's a very simple formula, but the actual understanding of it can take a little doing. I don't know, maybe you found it super easy, maybe my explanation was overkill, but I think it's important. It's really important to understand this concept because it underpins a lot of graphics programming in general. Just the idea of rotation is essential, especially in 3D. So that's why I took a little time to do this one. I hope it was semi-coherent. So next thing we're going to do is we're going to learn how to clip our lines to the viewport in an efficient manner. And we are going to create a little map, a little world for our space dong to fly around in. And so stay tuned for that. It's going to be fun. And I hope you enjoyed the video, and please, if you liked it, push the like button. That'll help me out a little bit. And stay tuned for the next episode as we continue on with more mathematical hijinks. See you later.